Hey, it's Brandon from STEM Tutor Club, and in this video, we're going to go over a worked example of a problem where we have to find certain values to make a piecewise function differentiable. So let's jump in. So this is the exact problem that we'll be dealing with, and you can see that they're giving us a piecewise function with two unknowns here, m and k, and then they're asking us to find what m and k have to equal to make this function be differentiable at x equals 1, at the transition point of the piecewise function. Because no matter what m and k are, they're automatically differentiable everywhere else, right? For this function, no matter what m is, it's a polynomial, so it's continuous and differentiable. Same thing here, even though it's a square root function. The only place where it could possibly not be differentiable is at the transition point. So we need to choose m and k to make it differentiable there. There are other versions of this problem where they don't have like the m and k. They just give you a function without any unknowns, and they just ask you, is it differentiable at x equals 1? That's slightly easier, but here they're asking us to find two values, m and k, to make it differentiable. Now you can solve this problem completely by hand without a calculator, but first I think it's interesting to take a look at this on Desmos. So let's hop over there. So here you can see that we have a pre-built Desmos animation basically representing this problem. And you can see that I've built two piecewise functions. You can do piecewise functions on Desmos if you didn't know how. You have to write it a little differently than normal. Normally you write the function and then a comma and then the domain when you're just writing them out by hand. In Desmos you have to write the domain or the subdomain. So in this case, less than 1, it'll be the red function. And then you have to do a colon and then the actual function. And then also, obviously, I have sliders down here to change m and k, and that's going to change what the functions look like. And I represented it in this case as two separate piecewise functions just so I could color them differently. But you could also put these in the same one. So here, what you could do on Desmos is you could just start randomly guessing. Basically, you could try values. So we can tell just by looking at this, m equals 1 and k equals 1 definitely doesn't work. This function is definitely not continuous at 1, and it's also definitely not differentiable at 1. But if I play with certain values, you can see, okay, so k seems to, it makes sense. K would scale the square root function, so that makes sense. Whereas m would kind of scale the square function. So for example, if I made m 2.5 and k 0.5, that would make this function continuous. You can see they are touching now at x equals 1. There are a lot of other values that would make this work, by the way. So like 3 and apparently 3 and 1 would also work. Or maybe, let's say 4, and you can also type in the values, 4 and maybe 2. Yeah, 4 and 2 also work. And there are a lot of values that make this function continuous, basically forcing them to touch at x equals 1. But what we need, remember, we want to make this function not just continuous, but also differentiable. What does that mean? It basically means there are no sharp corners. So right here, for example, you can see that there's a sharp corner. They do not have the same slope right there. So here you can see that if we zoom in especially, you can see that, yeah, there's like a sharp corner right here. And a sharp corner, by the way, means that the left-sided derivative, which is basically the slope as we come in from the left, is different than the slope as we come in from the right. So in order for this to be differentiable, for the derivative to exist, there needs to be no sharp corner, which is effectively another way of saying that the slopes as you come in from the left and the right have to be the same. So that's kind of the idea. And then again, I can kind of play around with different values. So if this is the slope of the blue one here, I can play around with k. Actually, let me bring k down here to just 1 again. And if I change m down here, I don't know, if I go down, and this is, I don't know, this is roughly correct, it looks like. But if you imagine the slope here, so the slope here is like this as we come in from the left, and the slope here is maybe not perfect, but it's roughly the same. The problem is, obviously, we have a discontinuity here. Our job is to find the m and k values that make the slope as we come in from the left and right the same, and make the values the same. That'll make it continuous and differentiable. So that's our goal. And we can find this completely by hand, so let's jump back over to our board to figure that out. So to do this problem, the first thing to keep in mind is that differentiability implies continuity. So in other words, if your function is not continuous, it's automatically not differentiable. Your function has to be continuous before you can even talk about whether or not it is differentiable. So when they're asking us to make this function differentiable at x equals 1, what they're really saying is at x equals 1, make the left-sided and right-sided derivatives the same, and make the left-sided and right-sided values the same. again, at x equals 1. It only matters at x equals 1. So what you do here to actually solve this problem, all you have to do is take these initial equations. So mx squared minus 2, this would be, for example, the left-sided function, the left-sided version of the function if we're slightly to the left of x equals 1. And then basically what you can do is just take this, so I'll say m, and then you evaluate it at 1. And whatever you get is what you get. And then on the right side, you would do the same. So basically, we would have k times the square root of 1. These need to be the same. And as I work these down, you can see that I get m minus 2 equals just k times 1. And then if I rearrange this, I can get m minus k equals positive 2. Now, this is not, and this is kind of what we saw beforehand, right? Remember that when we were talking about continuity, the functions touching at x equals 1, it seemed like as long, like 2.5 and 0.5 worked. 1 and 3 worked. 2 and 4 worked. That's what this is telling us, basically. Anything that where m is exactly 2 greater than k will work. And that's exactly what we saw in Desmos. So this is one constraint. So there's an infinite number of solutions, m and k, that would make the function continuous, but there should be only one of these that will make it differentiable at the same time. Now, how do we tell if it's differentiable? It's a similar strategy, except we first take the derivative of each of these and then set them equal at x equals 1. So if I take the derivative of this, if I first calculate that, the derivative of m times x squared minus 2, hopefully it makes sense that would be 2mx. And then over here, using the power rule, remember m and k are just constants. So m, you can just pull that out. What's the derivative of x squared? 2x. So 2x times m, I'm just writing it, 2m times x, same thing. And then here, similar situation, hopefully it makes sense why this would be k over the square root of x, basically by using the power rule. And you can think the power rule here. So if I have k times x to the 1/2, you can think about this. Or actually, sorry, there should be 1 over 2, I mean. So if you think through this, multiply by 1/2 out in front, and then x to the negative 1/2, negative 1/2, x to the negative 1/2, a negative and a fractional exponent. That's effectively what I have here. So hopefully that makes sense. But that's kind of the idea. This is just taking the derivatives of each of these functions. But remember, they need to be equal, not in general, not at every point. That's impossible. They need to be equal when x is equal to 1. So if I switch this to when x is equal to 1, that is what we need to be true. And if you think about it, as we solve this, this will lead us to another constraint that we can use to find the actual values of m and k that work. So if I solve this, 2m, and then over here, I'll get, square root of 1 is obviously 1, so I'll get k over 2. And then if I simplify this, we can get another constraint that basically 4m is equal to k. Again, so apparently whenever k is exactly 4 times whatever m is, and again, we kind of saw this. If you remember the things we checked with Desmos, we tried 0.2, 1/5, and we tried 1, and we got pretty close. Apparently, this is saying it was a little off. If we tried 0.25 and 1, that would have been perfect. So that's kind of interesting. So we saw something like this. But basically, there's also an infinite number of m and k values that would satisfy this equation. However, there should be only one value that satisfies both of these at the same time. So if you want to solve this, we need basically both of these constraints to be the same, or we need both of these to be true at the same time. So the way you can figure this out is you can basically take this k value, plug it in for k right here, and think about what we get. We get m minus 4m, because remember, that's what k is. So 4m is equal to k. And then that thing has to equal to, so this would be obviously 1m minus 4m, that's negative 3m. So negative 3m equals 2. And then as I scroll down here a bit, you can see that we get m equals negative 2/3. And then you can find the other, there are a couple ways that you can find the other one. So you could, if I just, for example, take this, you could just take this value, and this would probably be the easiest. You could also do it over here, but the easiest would probably be to plug that in. Now that we know what m has to be to make both of these true, we can plug that in here, and hopefully it makes sense that k would have to equal negative 8/3, basically 4 times this, negative 8/3. So apparently, these are the two values that would make the function, that would basically make the function on the left and right equal each other at x equals 1, and also the derivatives of the functions on the left and right equal each other at x equals 1. So now let's hop back over to Desmos to verify if this is true. Okay, so if we come back over to Desmos, and if we type in, for example, -2/3 here, and then for m, and then we said -8/3 for k, you can see that, yeah, that actually does look like it works perfectly. So here they're definitely touching each other. They definitely line up at x equals 1, so that's good. And also, if we zoom in, you can't, if they were colored the same, so for example, if I made them both blue, you wouldn't even really be able to tell the difference. It looks like the same slope. There's definitely no sharp corner. The slope as we come in from the left is equal to the slope that we come in from the right. There's obviously a hole on this graph, but that's being filled in by the left-sided graph. So yeah, this piecewise function is now differentiable at x equals 1 if we choose those two values. And by the way, if I change these at all, so if I change this, let me just change this back to a decimal. So if I change this at all, you can see that now it breaks down. And if I change the other one at all, it would also break down. So apparently -2/3 and -8/3 are the values of m and k, the only two values of m and k, by the way, that would make the functions on the left and right equal at x equals 1, and the derivatives of the functions equal at x equals 1. Both of those are required for the function to be differentiable. So that's it. Hopefully all that makes sense. That's actually all you need to be able to solve a problem like this. If you're interested in why this strategy works, though, stick around and we're going to go deeper into why the process that we use to figure this out actually makes sense. And we're going to dive deep into the theorems. So if you're interested in that, be sure to stick around. Okay, so now we're diving into why setting up these two constraints actually worked to solve this problem. I think it's actually easier to start on the right-hand side. So we already talked about the fact that differentiability implies continuity, which is why both of these have to be true at the same time. But why is taking the derivative of the first one, plugging in 1, and then taking the derivative of the second one and plugging in 1 for x, and then setting those equal, why is that the correct condition here? Well, you have to think about it. Effectively, what we're doing, another way to word this, is forcing the left-sided derivative and the right-sided derivative to be the same. And you can see these are the definitions. This is right here. This is effectively the limit definition of the derivative in both cases. The only difference is that the left-sided derivative approaches 0 from the left for delta x. So in other words, we're checking the slope as we come in slightly from the left. Here you can see a plus sign. Same idea, we're checking the slope as we come in slightly from the right. That's the only difference. So why do these have to be true for the function to be differentiable? Remember, the word differentiable literally means the derivative exists. Now what is that? Why do we say it like that? Why do we say the derivative exists? The reason is because the derivative is a limit. It is literally the same as a limit. In fact, here's the limit definition of the left and right-sided derivatives. The derivative is a limit, literally. We just use special rules most of the time, so it's easy to forget about that. But yeah, every time you use the derivative, you are using a limit. You're just remembering rules, so you don't have to actually solve it using the steps you normally need to for limits. But if it is a limit, remember that a limit only exists if the left-sided limit and the right-sided limit both exist and are the same number. That is why we have to do this. In order for the function to be differentiable, that means the derivative exists. The derivative is a limit, so in order for the derivative limit to exist, the left-sided derivative has to equal the right-sided derivative. That is effectively what we're doing here. So now you can still use the derivative rules, which we did in the problem. You don't have to actually solve a limit expression, but under the hood, behind the scenes, that is why this works. That's why you can just take the derivative of this, plug in x equals 1. That is effectively calculating the left-sided limit. And then same thing here. This is effectively calculating the right-sided limit, because this function is the valid function as we come in slightly from the right. If you set x, for example, equal to 1.01, this is the function you'd be using, because that's technically coming in from the right. It's technically greater than 1. Here, if you set x to 0.99, for example, slightly less than 1, you'd be using this function. So hopefully that makes sense. So that explains this condition. Remember, differentiability implies continuity. So in order for a function to be differentiable, it must also be continuous. That's why we come up with this constraint. But why does this constraint prove that it's continuous? Basically, if you think of the definition of continuity, so now we're getting into the definition of that. Basically, the definition of continuity is that f of c, in this case c equals 1, so f of 1 is defined, and then this is the limit exists. And when we say the limit exists, that really, you can think of that being broken apart into this larger, like this right here. You can think of this really including this over here. So this is kind of used in two places. And then basically the limit and the value of the function both have to exist. Now, you might wonder, why is this the definition of continuity? Well, basically, if we just focus on part two, if the limit exists, what that means is that if you come in from the left and right, you're getting closer to the same value. Well, you could have a hole. Remember, even if you have a hole, the limit still exists. So this is what we're saying when the limit exists. And then part one, or part three actually, is basically saying that, well, f of c, the value of the function, which we usually represent as a dot, must also be defined. And this is number one. And they have to be the same. That's effectively what number three is saying. So the way I think about it is the definition of continuity, the official definition, is basically saying the limit exists, and then we have the function fill in the hole. And you can see if I don't fill in the hole, then the function's not continuous, because as I come through here, I have to pick up my pencil to get over the hole. But if we have part three here where they're equal, then I fill in the hole, so to speak, and then I can't, or it's not going exactly where I want, but you get the idea. I can now go through this without picking up my pencil, and now it is continuous. So that's why the definition is the way it is. So effectively, when we come up here, basically what we're doing is we're proving that the limit of the function exists. It's kind of the same logic on the other side, except instead of the left-sided and right-sided derivative, it is the left, like as limits, it is the left-sided and right-sided function itself. So that's what we're evaluating here. This is what we're evaluating there. If these are both the same, we are proving number two, that the limit exists because the left-sided and right-sided limit are the same. And kind of at the same time, what we're doing, when x is less than or equal to 1, for example, so you can see here, whatever this bar is associated with, it could have also been here. But for one of these, when x equals 1, that has to be part of the function. So if you think about it, in this case, when x is less than or equal to 1, we're dealing with this function. So that means when we evaluate the left function, we're doing two things at the same time. We're calculating the left-sided limit of this piecewise function, and we are calculating the value of the function at x equals 1. So we're proving that, and then when we calculate the right, that's what we're doing here. If these happen to be equal, then that means two, the limit exists, and also it means that the value of the function exists, and they are both equal. So this simple equation here effectively uses the definition of continuity to prove that it's continuous. And if these turn out to be the same, then the function is continuous and differentiable, or it is continuous and the derivative exists, I should say, and then that means the whole thing is differentiable. Therefore, we can prove that the limit exists and that the function is differentiable at x equals 1. So it's connected and there are no sharp corners. So there you go. That's the in-depth reason for why this strategy works, in addition to how to actually use this strategy to solve problems like this. If you're interested in any other tutoring like this for AB or Calculus AB or BC, be sure to check out our links in the description at stemtutorclub.com. Thank you.